Hi, my name is Tom and you are at level 27 in mastering Einstein's special relativity. This episode is all about time dilation. Let's get into it. Let me see. Classic time dilation, or I would say time dilation when you go online and you see stuff on time dilation or you read stuff about time dilation. That's the time dilation I call classic. The setup is as follows. We have a house, and in this house is a clock, and we as viewers are in this house. There is a train, and the train has its own clock with a blue dial. And the train is moving very fast, 80% at the speed of light. If you want to know how fast is 80% of the speed of light, well, it means that each second this train could travel the world around about 6 times. So that's pretty fast, right? And what we are going to do is we are going to observe what the clocks will do when this train is moving at this speed. So here they are. I've frozen time, and when the train passes our house, we are in the house, then they sync their clocks. And when I push the button, then the train will run at 80% of the speed of light. Here it goes. And watch the clocks. Watch how time passes on our clock with the red dial and how time passes in the train with the blue dial. It's not the same. In our house, in our world, 1 minute has passed, 60 seconds. But the clock in the train did not go for 60 seconds. In this case, 36 seconds. And yes, it traveled a very long way. So the stationary clock, our clock, 60 seconds. Time dilated clock, 36 seconds. So a moving clock ticks slower from our perspective, from the perspective of the person not moving. That second part is really important. So I'm going to say it again. Moving clocks tick slower from the perspective of the non-moving observer. In this case, from the house. If you want to calculate how much slower, you can use this equation, but you can forget about it. This is an A level, so I don't want to put in mathematics in there. But this is the formula on how you can calculate how many seconds will have passed in the train based on how many seconds have passed in our house. Time dilation. Et voila, that's what it is. Now let's make it real world, because we can't be in the house and in the train at the same time, right? I can only be in one place at a time. I'm in the house. So how do I know what time it will be in the train? I could use a telescope and watch it. And that's what we are going to do right now. And that's what I would call real world time dilation. Before we go in, let's do another example. Let's see planet Earth and Mars. It's New Year's Eve on both planets at exactly the same time. They have a clock that has been synced. So the clocks are exactly at doing the same thing, and we are celebrating New Year's Eve. We Earthlings are celebrating and the Martians are celebrating. The distance between these two planets varies, but it's around this number on average. It's 12 o'clock, hooray, fireworks on planet Earth, and it's also 12 o'clock on Mars. And here are the fireworks on Mars. And let's say we have an observer on planet Earth looking at Mars. Will that observer see the fireworks when our clock, Earthlings, is at 12? Think about it. No, it's not. Why? It takes time for the light from Mars to travel all the way to our telescope. In fact, it will take about 12.5 minutes before the light of the firework reaches the telescope. So at 12 o'clock Earth time, we will see the clock of the Martians 12.5 minutes before 12, and that's what they didn't lit up the fireworks. And when our clock, Earth clock, is at 12.5 minutes past 12, then we will see the fireworks on Mars. And this effect of that light needs time to travel back to the observer is not in what I call classic time dilation. It is in real world time dilation, and we need a fix to calculate in this factor. So here we have the house, here we have the train. The train is moving at 80% of the speed of light, and we will watch the clock on the train as it moves. And let's see how that, oh yeah, and we also will have a observer in the train watching our clock. And I've done 2 animations, one for the left observer and one for the second observer. And you will see how crazy this gets. This is really, you can't think these things, you know, it's I don't know the words. Let's see the animation. Here they go. Oh, the animation jumped, but you get the picture. So 60 seconds will pass on our clock in our house. Einstein tells us that 36 seconds will pass on the clock in the train. But when we look through our telescope, because of the time delay, we will see only 20 seconds have passed. 20 seconds. So imagine you're a researcher and you don't know anything about relativity or special relativity, and you actually see 20 seconds in your telescope. You will write down in your experiment, when our clock is at 60, the clock on the train is at 20. And you would be wrong, because it's 36. Einstein is right here. It's 36, it's not 20. So you just can't even believe your eyes. Crazy, right? If you want to calculate, you know, what the number of seconds is in the telescope, you will have to divide the 36 seconds in the train over 1 plus V over C. So in this case, 1 plus 0.8 or 1.8. And 36 divided by 1.8 is 20. So this is what you will see on the clock. Let's do it for the other observer. Oh, no. Before we do this, a question that pops up is, if time actually slows down in the train, does that mean that the people on the train live in slow motion? No, they don't. You know, it's you know, it gives you headaches, this time dilation stuff, but the people on the train, they don't experience any slowing down of their clocks and their lives. On the train, just everything slows down, and that's why they don't notice. Even the pace in which they age slows down. Really? Yes, really. The people on the train are not 1 year older when 1 year has passed in our house. It will be a little bit less. Really? Yes, they will age slowly, but because everything is slowed down in their world, they don't see the difference. But from our point of view, from the house, we do see the difference. Let's switch the perspective around to make this story even more crazy. Now we are going to watch how the world looks from the perspective of the train. The train says, I'm not moving at 80% of the speed of light. I'm not moving at all. I did see a house flying by at 80% of the speed of light, and it had a red clock, and I'm watching that red clock in my telescope. Let's see what happens. So here's the house rushing by at 80% of the speed of light. We will do this for 36 seconds. I see my animations do not, at the end they don't sync. You have to imagine that all the clocks stop exactly at the same moment, of course. So 36 seconds have passed on the train. Real. We are in the train. Our clock tells us 36. But, here it is. But the number of seconds in the house will have passed 21.6 seconds. Ooh. Yes, because moving clocks tick slower, you know. And from the perspective of the train, the house is moving. So the house clock is moving slower. But the house, the people in the house will say, no, your clock is moving slower. The people in the train will say, no, your clock is moving slower. And if they look in their telescope, it's even worse. In the telescope, they only see our clock in the house at 12 seconds. I still don't have the words, how crazy this is. So you get this conversation. These two observers, these researchers, they meet and they don't know anything about relativity. Let's say they don't know anything about relativity or special relativity. And this person says, when my clock was at 60 seconds, my intuition would tell me your clock is at 60 seconds as well. But then Einstein came along and he told me, it will be 36. So I decided to pick up my telescope and see if it was 36, but it was 20. And then the other researcher says, well, if Einstein is right, my clock at 36 seconds, my intuition told me that your clock would be at 36 as well, right? But Einstein told me that your clock is slowing down, so your clock will be at 21.6 seconds. So I also decided to pick up a telescope and I saw 12 seconds. So really imagine this would be a true, actual conversation between two scientists. And they took pictures, They taped it with a video, what they saw on the telescope, and they are comparing the videos. Two things can happen in that situation. One, they will have a breakthrough and bring science to the next level, or it's a bar fight, they are gonna fight like hell, because it's really difficult if you see these numbers and you have pictures to tell you the truth. Well, in fact, the truth is somewhere in the middle. It's what Einstein says. Classic time dilation is the truth. So you can't trust your eyes. It gives you a headache, But this is time dilation for you. Classic time dilation and real world time dilation. I've made many other videos on special relativity. I built them up from the ground up in different levels. You can pause the video and look at this table. I have two of these tables. These are the first 18 and this is the second batch. We are now at level 27A. If you just want to follow the main lines when it comes to special relativity, you could only watch the green lines, I would say. But if you want to know more and fully understand it, I strongly recommend that you do the levels in between as well. And talking about the next level is 27B. Again, I will do classic time dilation, real world time dilation, but I will use the space-time diagram so you can actually see why this is. And it's a difficult graph, but it's, I would say, far more intuitive than the conversation we just witnessed. So I hope to see you there, and I thank you for watching.